So let me give it, so I'm gonna give you an abbreviated version of this thing I left us with last time. If R is a finite community ring, and A is an element of R, then A is a zero classer for a unit. So we went through some pains to actually show this last time. And in fact, we showed this in a more general setting. If you have a finite ring that has no left or right zero clasers, then you're right. Right. If there's no left or right zero clasers, then everything is a unit. So here's what follows from this. This is a very famous result. Corollary. If R is a finite integral element, then R is I'll give you a brief proof. X R is our finite integral domain. Then either X is a zero divisor or a unit. So X is not zero, then X must be a unit. Because there is no non-zero zero divisor in an integral domain. So we know that R is an integral domain, so there aren't any non-zero zero divisors. So if you have a non-zero element, it has to be a unit. Since any non-zero element has a multiplicative inverse R. So this is a very famous finite integral. So, any questions? Yes.
How does that conclude the R as a field? If it has a multiplicative inverse, how does that's just a definition of a field or?
A field, so there's many definitions of a field. I think the one I gave you is if you toss out zero, you get a multiplicative group.
Yeah.
And that's what you got there.
Oh, yeah.
Because everything has an inverse.
Okay, thank you.
Okay, definition. Okay, one of the big things that we study with linear groups are subgroups, right? I mean, yes.
I'm sorry, with the field thing, do we also need to have commutativity for the field?
Oh, right, but if you're an integral domain, you're automatically a commutative.
Oh, sorry, got it. Thank you.
Yeah, there's two things a lot of people overlook about integral domain. Commutative ring has identity. Everybody focuses on the no non-zero zero divisor, but don't forget it has to be commutative with identity as well.
Thank you.
Okay, one of the big things when we study algebraic objects is we study their subobjects, groups, subgroups, rings, subrings. We haven't defined subring yet. What do you suppose a good definition is? Intuitive. What should a subring of a ring be?
Ring with it.
A ring within a ring. That's a great way to put it, right? And that's what we're going to do here. So let T be a ring. A subring of T, I'll call it R. Well, okay, a subring, T is a ring, that makes it a group first and foremost, right? So you know what? I bet a subring should probably be a subgroup too, right? So back to the basics. Is a subgroup of R, I'm sorry, a subgroup of T under addition. Okay, but that's probably not enough because if you have a ring T, then it's a group and it's probably got a bunch of subgroups. What else do you suppose needs to be true of R for it to be a subring, to be a little ring within the ring?
Zero is subgroup.
Okay, not a subgroup, but we'll say this is a subgroup of T under addition that is closed under multiplication. That is to say, if R1 and R2 are in R, then R1, R2 is in R. Right? And so what does that do? That makes R, this makes R a baby ring. Because what is true about R now? I know it's a subgroup under addition. I know it's closed under multiplication. Now you might be wringing your hands a little bit, if you pardon the pun, because you might worry about, aren't there all these other things about rings, the associativity and all that. But remember, our assumption in the first place is T is a ring and R is inside it. So the multiplication in T is associative. So it's going to be associative with T. The multiplication distributes right in T. So it distributes in R. So all that other stuff, we're good to go. All you need is a subgroup that's closed under multiplication. Right? Often we demand that if T has identity, call it 1T. So if T is a ring with identity, then 1T is an element of R. So oftentimes people that are concerned with rings with identity, they don't call it a subring unless that subring actually contains the identity. So let me show you where they come up. What are the subrings? Well, we get lucky here, as a matter of fact, in a certain sense, because the first thing I got to do if I want to, the first sort of logical thing for me to do is ask myself, what are the subgroups of Z? Because for it to be a subring, first of all, it's got to be a subgroup, right? Anybody remember what the subgroups of this are? Anybody remember what's special about Z? What kind of group is it? What's it now? Right. But it's even, there's something that's even more restrictive than abelian that you can say about this.
Cyclic.
There you go. It's cyclic, right? And one of the things I remember from group theory is any subgroup, cyclic group is cyclic. So from that perspective, I can tell you exactly what the subgroups of Z are. There's a pretty boring subgroup there. Subgroups are all generated by a single element. So you can actually index them by the natural numbers union zero. This is sort of 0 times Z, 1 times Z, 2 times Z, and so forth. So the even integers, the integers that are multiples of 3, 4, et cetera, et cetera. These are all also subrings. In the general sense, right? So for example, take 3Z. What happens if I take two multiples of 3 and multiply them? Is it still a multiple of 3? Sure it is, right? So this is closed up under multiplication, right? These are all subrings. They are not. Only Z is a subring if we demand a subring contains the identities. There's no in this list here. This subring here, the whole ring is the only one that contains the identity. So if we make this second demand, this has only the subring itself. Here are some other examples. There's lots of Z is a subring of. I'm gonna use a symbol here. Here's a ring you may never thought of before. This is all the rational function, or I'm sorry, rational numbers that have an odd denominator, right? Notice that every integer is one of these because every integer, call it K, can be written as K over 1, right? Let me ask you something. What happens when you add two fractions and they both have an odd denominator? What can you say about the new denominator? Still odd. Right? So this is actually simple, right? Because when it's closed under addition, the minus sign of something with an odd denominator has an odd denominator, and you can check all the things. This is actually subgroup. This is also closed under multiplication, isn't it? Because if I multiply two things with an odd denominator, what do I get? New fraction, odd denominator. This is actually a subring, or I'm sorry, Z is a subring of this. And this is a subring of the rational numbers. Notice it is a proper subring. What's something that's in that weird middle ring that's not in the rational numbers? Or that, I'm sorry, something that's in the rational numbers, but not in the weird middle ring. 1/2, for example, is here, but not here. Here's Q, on the other hand, sits inside of this larger ring. This is the ring of everything that looks like rational plus rational radical two. It may not be quite obvious that this is a ring, but let me kind of try to convince you. If you have A plus B radical two, and you add C plus D radical two, here A, B, C, and D are all rational numbers. If you were in high school, your teacher would probably say, add this up and group the things, right? Well, we'll do that. Some of the two things still in them, right? Is it clear that the negative of this is just change the sign on both of them, right? And the difference of any two things is in there. This is actually a group. Everybody okay with that? Under addition. And it's also closed under multiplication. That might be, you've got to do a little bit of computation here to show it's still closed under multiplication, but it's true. What happens when you multiply this? Well, you get AC plus AD, B radical two, plus BC radical two. And the last term is 2ABD. Sorry, 2BD. Now let's group this again. This is AC plus 2BD plus AD plus BC radical two. Notice that's still in because A, C, B, and D and 2 are all rational numbers. So this mess right here is just a big fat rational number. And this is a rational number. So it's still in there. It's rational number plus rational number radical two. This is actually a ring. It is a subring of the real numbers. By the way, there's a huge jump here. There's lots and lots of things in between here. This is a subring of the complex numbers. Anybody think of a ring that's bigger than this? How about all polynomials with complex coefficients? That's a bigger ring. Anybody think of a bigger ring than that? I can go crazy with this. The set of F from C to C such that F is continuous. All continuous functions from the complex numbers to themselves. Certainly every polynomial is a continuous function. And I can go further than this. Right? There's always a bigger ring. But everybody see how these all have ring structures. They're basically, they're groups under addition, closed under multiplication, and they're kind of getting bigger and bigger. These are all good examples of subgroups. Yes.
Are you just using the subset symbol to say subring, or is that like a different name?
Subset to say subring.
Okay.
That's right. Okay. Now, this is a good kind of segue here. Okay, so now we're ideally getting back to your question here. Ideals and homomorphisms. So when we looked at groups, our first algebraic structure, then we talked about subgroups. Okay, it's a little baby group inside the parent group. But you know what? There were some subgroups that were better than others. Right? What were the, anybody remember what's the special kind of group that probably got more attention and significance? The normal ones, right? The normal ones had a little extra condition, right? They were preserved under conjugate, right? And of course, that just looks like I'm making up crap so that I can give you homework problems, right? It seemed probably at first like an artificial condition, but it's actually important because normal subgroups is what turned out to be the kernel of homomorphisms. So they control the way homomorphisms work, things like this. That's why they're important. Subgroups, it's not that they're not important, they certainly are, but the normal subgroups are the real ones. There's a similar thing that goes on with rings. Okay, so you've got the notion of a ring. We know what a subring is like. But subrings aren't really the most important thing. There's a more important type of general subring, and it's called an ideal. Right? You might think of it as an ideal subring. So the concept of ideal, you should think this is sort of the intellectual companion of what a normal subgroup is for a group, what an ideal is for a ring. But what I'm going to want to do first is this. I am going to start this actually with the notion of homomorphism first. Well, actually, you know what? I think I might break that pattern here. Definition. I'll just let's a little more generally. What are the a subset I in R is called I'm gonna do this a little bit more generally than I'm gonna do in class and practice. I'm gonna start you with the most general notion. It's called a left ideal.
Yes.
If number one subgroup under addition. And number two, for all alpha in R, alpha I is contained in I. Let me reinterpret this for you. Alpha X is in I for all X. And I alpha. So what makes an ideal is it sucks. It's a vacuum cleaner, right? When I hit anything in R, or I'm sorry, when I hit anything in I on the left by something in R, it's sucked into I. So it's like a little vacuum cleaner, right? This is what it means to be a left ideal. Let me make some notes on this definition. R is commutative. Left ideal, the right ideal is an ideal. That's a rather complicated sentence structure there. Let me tell you what I mean. When I say a left ideal, it means it sucks in from the left. There's an analogous definition. There's a right ideal. It sucks in from the right. If the ring's commutative, the order of the multiplication doesn't matter. That is, if X is in I and alpha is in R, then X alpha equals alpha X is in R for all. Yes,
What you said about like it takes something from I goes to R?
right. When you multiply anything, if you take any element in X, or I'm sorry, any element in I, and you multiply it by any element in R, it sucks it back into I.
Okay.
So for example, so an ideal is actually is a subgroup of R in the general sense. That is, I don't demand that one is in there. That is closed under multiplication by elements in R. It's a little bit more. Notice the subring only has to be, you only have to be closed under multiplications within the subring itself. An ideal is closed under multiplication from outside. If you take something in the ideal, something from maybe outside the ideal, multiply it, it goes back into the ideal, right? So it's a little, this is the little bit of strength that makes an ideal a stronger thing than a subring. Because subrings, if you multiply two elements of a subring, it's in the subring. But if you take an element of a subring and multiply it by something not in there, it might not be in the subring. Ideals suck things in. And that's the normal part. That's the part that makes it a little bit stronger. Right. So let me give you an example. Actually, the example that I am going to use here worked for any n. I'm going to do it for 3 just so we can kind of see things better, right? This is an ideal. Okay, yeah, we've already sort of argued that I is in fact a subring, right? Because the integers that are multiples of 3 is a subgroup, right? And when you multiply any two multiples of 3, you get a multiple of 3, right? But more than that, and if K is in Z and X is in I, then X is 3M. Right? Now the definition of living in I, X has to be multiple of some integer, right? Therefore, notice this is obvious, isn't it? That if you multiply any integer times a multiple of 3, that new product is still a multiple of 3. You still get that factor of 3 in it. That's why this sucks, right? It takes every integer and it sucks it into being a multiple of 3 when you multiply. So this is how an ideal works. Let me give you an example that might be a little more exotic. Exactly. Well, let's do this. Let's look at the set of functions from the reals to the reals that are continuous. This might be a flashback from days of old, right? Because we had these things all over the place when we were in calculus, right? For example, any polynomial is in here, right? Any not any trig function, but for example, sine x is in there, cosine x is in there, the exponential function is in there. The natural log of the absolute value of x squared plus 1 is in there. So this is full of all kinds of nifty functions, right? Okay, is this a ring? Well, first of all, is this a subgroup? Let me ask you this. What happens if you take two functions, f and g are both continuous, and you add them up, what do you get?
Continuous function.
You get a new continuous function, right? That's, in fact, they probably, I'm pretty sure they didn't prove it to you, but they probably told you that calculus. You had two continuous functions, you get a continuous function, right? What happens if you multiply two continuous functions? Still a continuous function, right? So actually, these things, there's more details to show, but you know, the multiplication of functions over the addition is distributive. Addition and multiplication of functions is associative. The last part you probably learned in 3190. This actually forms a ring, and it's commutative, right? Because the way we're multiplying functions is we're pointwise multiplying, right? Like sine x times e to the x. There's no function composite. It's just e to the x times sine x, right? So this is a commutative ring. Do I agree with that? And it's got identity. What's the identity here? What function can you multiply by any function and it leaves it alone?
Just the identity function, everything to itself.
The function 1, like the function y equals 1, right? Because if you multiply pointwise 1 times anything, that's what you get, right? The identity function would be, that would be the identity if we were composing, right? But we're not composing, we're pointwise multiplying. Anybody pick out an ideal? And I am waiting for the smart aleck answer.
The thing itself is something you don't bring.
That was the other smart aleck answer. That's true. It turns out that any ring is an ideal itself, right? Because the ring itself is a subgroup of itself, and it's certainly closed under multiplication, right? Because the ring itself is closed, right? What's the other extreme of your example? 0, right? The 0 function is also an ideal as well. This is true in any ring that 0 is an ideal because it's a very silly way. It's a group and it certainly sucks everything in because anything times 0 is 0. Yes.
Wait, we're not talking, okay, we talk about inverses in this context. It's not like inverse functions because that would be composition, right?
That is correct.
Okay, we're talking like negative.
Right. And also the problem is there are continuous functions that don't have an inverse, like y equals x squared, for example. Well, it doesn't have an inverse. You might think of a more exotic values.
Polygon.
It's a great idea. Oh, and I like this too. The suggestion here was all polynomials. That's an inspired thing. It doesn't work as an ideal, but it is a subring, right? And I like your example because we can illustrate something here. Why is the set of all polynomials? Let's do that. Set of okay. Certainly, this is a great example because polynomials we know from our days in calculus, these are all continuous functions from R to R, right? Check. So not just blowing smoke, this certainly makes sense. What happens when we add two polynomials or subtract polynomials, we get a new polynomial? So it's a subgroup. Everybody okay with that? When I multiply two polynomials, by gum, I get a new polynomial. But why is it not an ideal?
To be able to multiply it by anything and see.
That's right. So for example, this is a subring for sure, but X is in P. I just took this simple example because X is a polynomial. And e to the X is in C, but X times e to the X is not in P. Right? So that's a great example of a subring that's not an ideal because the vacuum cleaner ain't working. This isn't a polynomial, right? Yes.
Like simple, is there no ideal subgroup or sub?
No,
Ideal, no ideal,
Oh, there's actually plenty of them.
there's plenty.
The's plenty. It's surprising, isn't it?
This is a
Right?
weird calculus answer.
Here's an example. This one is, and once you see that, I'm gonna give you one example, you'll see infinitely many, and there's more than that. Let I be the set of f of x, c, such that f of 0 is 0. Okay, the first thing I want to convince myself of is this is not the empty set. I do not wish to stand in front of you all at this hour of the morning and prove theorems about the empty set. So pray tell, is there something in here? What's one function that is continuous everywhere and is 0 at 0?
X. Everything.
Right. X works. How about this? Let me show you what a lazy critter I am. 0, right? The function y equals that is an example. Sine x, x squared times e to the x. There's lots of stuff in here, right? Definitely not in. Okay, so the first thing I'm gonna do is I'm gonna throw the subgroup criteria at it. Suppose I have F and G in here. I want to show f of x minus g of x is in I. And if I can do so successfully, this will mean that I is in fact a subgroup. But look, f minus g of x evaluated at 0 is f minus g evaluated at 0, which by definition of pointwise addition and subtraction is f of 0 minus g of 0, which is 0 minus 0, which is 0. So I is a subgroup. There you go. What about the, yes,
So that's like the subgroup criteria, right? The f of x minus g of
that's
x.
exactly right.
Okay.
That's the subgroup criteria. I know that it's not empty. So now I just tell you, if I've got two arbitrary elements, if there are differences in there,
Okay,
it's a
yeah,
subgroup.
yeah.
And of course, it's difference here because the group's abelian, right? As opposed to x, y inverse, it's
Yeah.
x minus y, if you will. 2, let f of x be an I and call something else, e of x in C. Now, consider e of x, f of x. My goal is to show that that animal lives in I. But p of x, f of x evaluated at 0 is p of 0, f of 0. And I don't care what p of 0 is. I do know that it's defined there because the functions are continuous everywhere. F of 0 is 0, so this is 0. So p of x, f of x is in I, And this is an ideal. It's,
So a little confused about the subtraction,
yeah. What, where? Right here?
the f of x minus g of x.
Right. So what we're trying to do is show that if you have two elements that live here, then the difference of those elements live in I. How do we tell if this thing, or in general, anything lives in I? You plug zero into it, right? And if you get zero, when you plug zero into it, it lives there. And that's what we did here. F minus G, plug in zero. This is F of zero minus G of zero, which is, so that means that the function F of x minus G of x lives in I.
Well, why did we need to show that? To show that it's.
To show it's a subgroup, right? That's the subgroup criteria. Other questions? Okay, so this is, and this is the, idea of, that's a good example. So, but then this example is contrast subgroups. Now, the notion of an ideal is very similar to that of a normal subgroup. And the big thing about the normal subgroups, one of the things that I made a big deal out of back in group theory is when you have a normal subgroup, it is the kernel of a homomorphism and vice versa. And that's actually where ideal one can construe in terms of this setting too, because that's exactly what happens here. But before I can talk about that, I need to tell you what a homomorphism is. So let me give you the following definition. And see now, this is where kind of some of the payoff comes in algebra, because the themes that we have repeat. Let R be replaced. A function, let's call it F. Is a homomorphism. And sometimes I'll call it a homomorphism if the context is clear. But what I mean here, when I set the definition. Okay. So what would I want to be true of a homomorphism of rings? Well, it should be kind of, again, intellectually paired with the notion of homomorphism of groups, right? The only difference with a ring and a group is you've got this extra operation. Anybody will take a stab at least one thing that should be true of a homomorphism of rings.
It's like group homomorphism for the additive.
That's right. First and foremost, R and T are both abelian groups. So whatever this homomorphism is, should respect that. It should be a homomorphism of the underlying group. So that'll be the first thing. I'm going to write it this way. F of x plus y is f of x plus f of y. For all x, y, and r. And this just means that f from R to T is a homomorphism of abelian groups. So homomorphism, what that does is that makes sure that this function is respected. It's given the respect to the additive structure, right? As you go from R to T, right? I don't need to be stopping here though, because yes.
That's not a question, keep talking.
I don't want to stop here because rings are more than just abelian groups. So what else do you think we should have going on? Yeah,
Scalar multiplication, I mean, like if I multiply by it.
very similar, but you don't have a scalar here, right?
Yeah.
Because, so let's do it this way. This first one focused on the additive operation. So the next thing I'm gonna do is I'm gonna focus on the multiplicative operation. What do you think? How are we gonna get this to respect multiplication?
Text in general form.
Good. Respects addition, respects multiplication. If you've got those two going on, then, this is what we call a homomorphism of rings. Note, like I did earlier with the subring thing, if one R is in R and one T is in T. So what we're saying here is R has an additive identity, and not additive. R has a multiplicative identity and T has a multiplicative identity. We often, I'm never gonna try to trick you. I'm never gonna like give you a problem and say, oh, psych, you were supposed to, you can always ask for clarity on this. We often require that F of the identity of R equals the identity of T. And there are actually mathematical reasons for that. I might give you a homework problem to kind of illustrate why I want that to happen. Let's look F from R.
Sounds kind of fun.
Actually, there are many ways to do this, but I'm going to do what I think is like the easiest one. Remember that thing on the right there is the 2x2 matrices over the reals under matrix addition and matrix multiplication. Can anybody think of a homomorphism? What is maybe the most natural thing to send lambda to? If I have a lambda in R, anybody think of a corresponding matrix? 2x2 matrix I can send that to?
It's with the determinant lambda.
Okay.
Fall under,
A good idea.
does that fall under addition?
That's almost like a cheat, isn't it? Fine. Notice this is a homomorphism of rings. It's certainly not onto, right? Because there's lots of matrices that you can't get in the image of this map. The image of this map always has zeros in these two entries, right? Always. Right? But notice that F of A plus B is A plus B, 0, 0, A plus B, which is A 0, 0, A plus B 0, 0, B, which is F of A plus F of B. So it preserves the addition. And also, and boy, we're lucky with this, I'm telling you, because matrix multiplication doesn't usually, it works nicely on the subset. If you look at F of AB, this is AB 0, 0, AB. And because these are scalar matrices, you can check very easily that this matrix times this matrix is this matrix. And this is F of A. F of A. There. Right. Also notice that F of 1 is 1, 0, 0, 1. So notice it takes the identity of the real numbers to the identity matrix, which is that nice property that. Okay. Any questions? There are other adjectives that I can apply to a homomorphism. For example, the homomorphism can be one-to-one, onto, it can be an isomorphism. Those adjectives about whether things are one-to-one and onto apply as before. Let me give you a final little proposition for today. Proposition 925. Let F R T be a homomorphism. Number one, the image of that, which is the set of F of R and R, is a subgroup. See? Check that. I think it's a good exercise to convince yourself that's true. And here is another big player, the kernel of that, which is all the crap in R, such that F of X is zero. That is the zero element of T is an ideal of R. So check those things out, and we will talk more about this. Actually, today's Wednesday. Today is Wednesday. Friday is the next day of class. We will not meet on Friday. I am going to post, I'm going to post, a video for you guys to watch, that I'm going to record probably this afternoon. I apologize for that, but I got to be a calculus challenge. You will have the office hours for TA on Friday. Other than that, give me a holler if anything comes up. It's going to be crazy for me, but I'll find it.